Good morning and welcome to this Verda Scientific webinar on behalf of Carbolite Gero. I'm Robert Pryor and I'm your host today. We'll be hearing from Tom Gould and Fabienne Uleman-Colley during the presentation, which will last just under 30 minutes. And there'll be a few minutes of questions and answers, so please do put those in via the Q&A section of GoToWebinar. Any questions we don't get through to, we will come to afterwards via email. Please note that all participants are muted during the presentation. So let me just first of all introduce you very quickly to Carbolite Gero, which is a member company. With over 1,000 employees and 22 offices around the world, Verda Scientific Group sets the gold standard in high quality control and R&D solutions in research institutions, analytical laboratories and cutting edge manufacturing companies. From sample preparation through to particle characterization and heat treatment, through to elemental analysis and hardness testing, our companies deliver significant benefits to your process, your outcome, your sustainability, and your profitability. 4 of the Verda Scientific companies are hosting webinars today. So far, we've heard from Ultra, Microtrack, and Wretch, and we're about to hear from Carbolite Gero. For anybody who's missed the previous presentations, they are being run again this afternoon, so please do sign up and join. Each of the organisations has many decades of experience in their specialist field and are well worth listening to. Don't forget that during the webinar, you can download valuable PDFs from the GoToWebinar software. That includes the PDF slides of this presentation. A recording of the webinar will also be made available in the next few days, and the link will be sent out as follows following today's webinar. I hope that after the webinar is concluded, you'll take the time to look around the various Verda Scientific websites and discover the wealth of information that's available. So at that point, it's now time to turn you over to Tom and Fabienne from Carbolite Gero for what I'm certain will be an informative session around the use of ovens and furnaces in the battery materials sector. Tom, it's over to you, and I'll return in around 20 minutes time to talk and to answer the Q&A section.
Thank you, Rob. Welcome everybody, and thank you for joining us today. I'd like to kick off by introducing Carbolite Gero to you all. We manufacture a range of systems from ambient up to 3,000 degrees, and these can be categorized into 4 basic systems. So we have ovens up to 700 degrees centigrade, we have hot wall chamber furnaces and tube furnaces up to 1,800 degrees centigrade. And we also have vacuum furnace systems that run up to 3,000 degrees centigrade. So as part of the Verda Global Group, that's constantly investing in developing new products, we also feature the new split tube and gradient tube furnace on the far right-hand side, as well as a range of custom designed furnaces to meet your requirements. So we're going to talk about batteries today, and specifically battery materials. First of all, what makes a good battery? The first 2 points, homogeneous and pure material. So this creates a longer lasting cell and also a more efficient power source. Ensuring the end product is lightweight allows for a more efficient system. A good crystal structure. So the crystal structure is important to ensure that the ions pass between the anode and cathode layers effectively. Ensuring that we have the right electrolyte is used, and this increases the energy density and the capacity of the battery. And finally, probably most importantly, safe materials. So ensuring that the right materials are used in a safe way. For instance, if you use pure lithium, this burns freely in air. So ensuring that you're not using materials that could potentially pose a risk to the user.
Yeah, thanks a lot for that, Tom. So mainly the applications with furnaces and ovens for batteries are synthesis of materials, graphitization, debinding, calcination, some drying materials. So if the materials are soil gel based, and also it is not a furnace, but it is machine learning. So the machine learning became very, very important due to the fact that there are databases existing where possible material combinations are sourced and then compared by a computer and by a KI. So that's why we would like to talk today about the additives, which are highly important to the materials, to the anode and cathode materials, so to prevent them and protect them from corrosion, to enhance the electrical performance, and to inhibit the dendrite growth. And dendrites, you might know about that. It is like a tree-like and needle-like material which might destroy the membranes of the cell. So this should not happen. So that's why it must be protected to control the freezing point, and also using perfluorinated electrolyte because they are very inert to other compounds. Materials of interest are especially today under research sodium, aluminum, and sulfur. Next slide, please. Thank you. So a battery consists of a casing that is steel or aluminum based, then cathode materials, which are LCO, NMC, NCA, LFP, or LMO. And below the table, there is written what it means like. So oxide materials. The anode is mainly graphite, but there are also developments in the field of silicon and other materials. The electrolytes, which are very important for the conductivity in lithium-based batteries. Then anode and cathode materials, aluminum, copper. The separator is the membrane, so which are mainly polymers, and additionally some additives, which are carbon black. So the weight percentage you have seen on the right side, so which is about 20, 25, 14, 10, 5, 5, and 1% respectively.
Okay, to start, we're going to look at the synthesis of graphite then. So in this case, we're going to assume that we're starting with a carbonaceous start material. If you do have a strong desire to learn a bit more about the full graphitization process, then please get in touch via the Q&A feature at the end of the webinar.
So as you can see in the diagram, we have multiple steps from the raw material to the final graphitized carbon material. So at the very beginning, we start with a highly disordered arrangement. So it becomes step by step more and more ordered up to 2000 degree, which is about the carbonization temperature. There are still some defects and some, let's say, three-dimensional arrangements available. And so then up to 3000, which is mainly between 28 and 3000 degree, the graphitization takes place. This is very, very important to ensure the distances between the graphite layers so that the ions can move freely. Next slide, please. So as mentioned before, multiple step process. So at the very beginning, an off-gassing and pyrolysis takes place. The pyrolysis is mainly happening between 200 to 400 up to 800 to 900 degree. In this stage, lots of off-gases are formed, so you need to carry them away. This is very important to have a safe and pure atmosphere inside of the furnace. Later on, the carbonization temperature starts, so there is some, let's say, rest debinding, so some off-gases like hydrogen, nitrogen-based compounds are expelled from the compounds as volatiles. So in the last step on the right-hand side, the graphitization takes place then above 2000, mainly 28 to 3000 degrees Celsius.
Okay, so to look at the type of systems that you need to run through these process steps, the main bulk of the work, or the main weight removal, is actually being done at relatively low temperatures. So we have hot wall systems that can facilitate this. So this is the pyrolysis and the carbonization phase. We can start with even things like small tube furnaces on the left-hand side. The main limitation with these is that you can only process a small amount of material. And we also don't have any means of dealing with the off-gases that Fabian's just mentioned. So there's a high risk of condensation in the work tube. These are, however, very flexible, low-cost systems. So they're good solutions if you're working with very small amounts of material up to 1,800 degrees. The bigger systems that you see in the middle, up to 1,300 litres, and these are very much configured for pyrolysis work. So they're very easy to clean. They deal with all the off-gases and burn them cleanly through the afterburner, giving you effectively water vapour and carbon dioxide as the residual off-gases. For graphitization, on the other hand, we've got a much more sort of high-end precision system. So as Fabian said there, we've gone through most of the late production phase. The off gases are residual; they're not too much of a heavy duty for the furnace. They feature graphite felt insulation, and they've got graphite heating elements. These systems will go up to 3,000 degrees centigrade, and that's measured using optical pyrometers. We use a combination of thermocouple control at lower temperatures and optical pyrometers to give us the best temperature accuracy through the process flow. We also incorporate an afterburner system to deal effectively with the off gases, and you can see that on the right-hand side of the first unit here. We actually have a white paper coming out, which will include some XRD analysis of some processed material. So again, if you've got any interest in the results of that white paper, then please get in touch via the Q&A. And again, if you've got any specific questions about graphitization, please post them and we'll come back to you with some responses. So moving on, we'd like to have a look at some other materials and processes that are important for the production of battery materials.
Yeah, thanks a lot for the introduction of the graphite furnaces and the pyrolysis furnaces, Tom. Thank you. We have picked up nickel as a very, very important battery material for the next years. It is like that cobalt and nickel are main compounds in lithium-ion batteries, and cobalt is, let's say, a very critical compound where the manufacturers would like to reduce the amount of cobalt, so the content, so that the environmental and humanitarian issues are decreased. So that's why the nickel must become more and more high concentrated in the battery cells. And an additional fact is for sure the higher energy density which you will receive with the nickel compounds. So if you would like to produce nickel in a big scale, it is like that nickel content is raised by the so-called flotation process. That means that a physical chemical process is taken place in water, and then there is a soap introduced into the water and some additional additives to make some ores floating in a foam on the top surface of the water to remove it from the rest ore of the nickel. So in the next step, the iron, copper, nickel ores, they are roasted with air. Then the ore is melted together with sodium sulfide, and only nickel sulfide remains. This is due to the fact that the copper is, let's say, forming a soluble liquid phase, and this is then easily physical separated from the nickel sulfide. The nickel sulfide oxidizes later on with air to nickel oxide, and it will be reduced afterwards with coke. The raw nickel then is electrochemically purified, or even to get a higher purity of the nickel, the Mond process is used in a high scale or in a high term scale. So in an industrial scale, it is like that there are very, very big towers, and the nickel carbonyl, because it is reacted with carbonyls or with carbon monoxide, it will be flown through a very, very big tower reactor, and at 400 degrees it will decompose, and deposition of pure nickel will take place.
Thank you, Fabian. So in this example, we were actually seeing what we call a seesaw furnace, and this is switching between roasting and calcination. The nickel sulfide is oxidized with air in the calcination phase to nickel oxide and sulfur dioxide, and then in the reduction phase, the nickel oxide is reduced with coke to raw nickel. So we have a batch system on the left-hand side, and the TSO actually oscillates. So it agitates the sample, and we've got zone control in there, so we can actually heat the two areas at different temperatures. And the mixing ensures a good gas absorption into the nickel as well. For continuous processing, we have the TSR rotating tube furnace. We've got a short video here just to show how that works. So as you can see, We've got control over the angle of inclination, and this helps to control the speed of the material as it flows through the furnace. You can also control the gas type, so we can process under an inert gas. And then we've also got specific controls for the rotation speed as well. So the rotation speed and the inclination are what give you your residence time in the work tube. The temperature can be split into several zones, so we can get a gradient through the furnace. And as you can see here, the materials can be fed either in batches, or you can have a continuous feed system with a variety of hopper and feed assemblies available.
Yes, thank you, Tom. So with respect to the step of the Mond process, so to make the raw nickel to pure nickel, I have explained before that there are big towers in an industrial scale used. In a smaller scale, there are some so-called ampules used, and therefore you need a gradient inside the furnace. And at lower temperatures, the raw nickel is reacting with the carbon monoxide. Then the carbon monoxide becomes gaseous because of a nickel complex material. It's nickel tetracarbonyl. This nickel tetracarbonyl is then circulating inside of this ampule, and at higher temperatures, it decomposes to pure nickel, and the carbon monoxide is then expelled. So therefore, it is like a cycle, and the raw material, so the impurities are laying still here in this case on the left hand side where we have written raw and 80 degree. So it is like a cycling process, and yeah, a very beautiful process to purify the raw nickel to the pure nickel.
Okay, so one example, as Fabian said there, we can do this on a very small scale. So again, for research level. The CVT process is best handled in what we call a multiple zone furnace. So the furnace has independent control through the length of the work tube. And if we look at the graph in a bit more detail, you can actually see how this temperature step sort of looks as we monitor the temperature through the furnace. So in this case, the raw nickel would sit on the left-hand side, and the pure nickel would sit on the right-hand side, with the zone barriers acting as an inhibitor for the heat transfer between the two areas.
Yeah, but not only nickel is very important in batteries, but also the research with respect to graphene, CNTs, which are carbon nanotubes, silicon, and other new materials. And why is that? The silicon graphite composites, they have a higher capacity and a higher density. So that if you would use pure silicon, the capacity of the battery would be 10 times higher because of the storage of the lithium. So silicon can store much more lithium. But there is a very critical factor, and this is the swelling. And when silicon starts to swell, it will destroy the battery. It might even explode. So therefore, there are composite materials under research. It is a combination of coated silicon with graphite. So additionally, there are materials like niobium tungsten oxides or niobium titanium oxides. And because of the oxides, they have, let's call it like a big cloud of electrons around the oxygen, around the oxides, and this allows to move the lithium easier and faster through the batteries. In this case, it is a solid-state battery, and here the fast charging might take place within 6 minutes. And therefore you could run your car about 320 kilometers already. And the lifetime of such materials are not well explored, but already explored with around 5,000 cycles. And the titanium oxide based material has a lifetime of around 20,000 cycles and the double capacity. So this is very interesting materials under development. So additionally, the composites materials, as mentioned before, are under research. It is especially the Wacker chemistry, where we sold a furnace to them. And the material which they are working on is the silicon graphite stuff. Let's say carbon is introduced like a powdered or flaked graphite and carbon, and they are introduced into the furnace. Then they are melted and pyrolyzed together with silicon. These composites materials has a more high efficiency, as mentioned before, and they are used mainly in cars for, like a smartphone as shown on the left side. It is, let's say, not so reasonable, so therefore the lithium-ion batteries are still very, very important and will take place and will stay for this field of consumer products. But on the right-hand side, you can see a car, and as you know, we need a high distance we can drive with the car, and we need fast charging, that the mobility will be implemented at a high base so that each customer can profit from it. So as you can see here on the left-hand side, there is the furnace, and there is a tray and a rack system with, in this case, there are some, let's call it crucibles or boats made from quartz. In there, the material is placed, so it is the composite material from silicon, carbon, and other stuff. Then it is heat treated under inert gas. And in the diagram, you can see there's a first step at around 300 degrees, and then the temperature is raised again up to a little bit above 600. So this is mainly the pyrolysis step, and especially to remove the off gases and to burn afterwards in an afterburner. And this is important to carry them away. And then there is the main sintering process up to 1000 degrees. So there the coating takes place. It can be done in a very small scale furnace, as you can see on the bottom right side. The bottom right side is a standard CWF furnace with a retort from us. And there some pre-testing were done. It worked okay, but this furnace is mainly not made for pyrolysis because the exhaust of this small furnace is very, very small. So there are some issues that lots of binder and pyrolyzed materials can condense, and then the gas outlet, the exhaust, stuck. And this is really not good for the process if you have an overpressure. So lots of things can happen. So therefore, you need a special furnace made for pyrolysis, and this is the one on the left top side. And Tom will introduce you to the furnace on the next slide.
Thank you, Fabian. Yeah, so the furnace in question for the specific process, you can see we incorporated a loading system that actually interfaces with the front of the furnace to make it easy for the operator to load and unload the quartz crucibles. It's a hot wall furnace, so the heating system sits around the outside of the containment vessel. And we had to incorporate a special gas system, which includes a gas safety system to deal with the hydrogen gas. And then also, in addition to this, we need to make sure, as Fabian said before, that we're safely removing not just the off gases, but in this instance, the residual hydrogen from the process to ensure the process is safe. So we're just about to wrap up, but if you have a specific process you'd like to review with any of the team, we have multiple test centres in our major markets around the world. And here the team can work with you to best understand the product that fits your process best. Yeah, so please do get in touch if you've got a specific application in mind that you'd like some support with. So yeah, just to summarise, Carbolite Gero, we've been around for 80 years, so there's 80 years of knowledge and know-how. And if you want to see high quality equipment, then please get in touch to discuss the applications, as I said, with the Solution Centre. And if you do, you'll see a wealth of benefit from a product range and process knowledge that's been developed by the in-house team, has been delivered by a world-class company, and it's supported by the Verda Global Group. So again, I'd like to thank you for your time, and I'll pass you back to Rob.
Thank you very much indeed there, Tom, and thank you very much indeed, Fabian, for that fascinating presentation. I've got a couple of questions that have come in, so I'll head straight to those. In the rotating tube furnace, what's the longest time you can process a material for?
Well, okay, so residence time in the tube furnace is quite tricky. So as I said, you can control this by increasing or decreasing the angle of inclination and by speeding the rotation up. That said, in a relatively small system,
Tom, you're muted. I'm afraid your microphone seems to have gone out of range.
Right, you're looking at between 30 minutes up to an hour. We do have systems that incorporate an auger system, so you can actually sequence the material through the furnace. But again, if the person in question would like to get in touch with us at the end, we can discuss their specific application, hopefully find the right fit for that.
Okay, thank you. Second question that's coming is, how do you accurately measure temperatures at temperatures such as 3,000 degrees?
Yeah, yeah, maybe I take over in this case. There are, let's say, two possibilities. On the one hand, we have calibrated pyrometers, which are working at high temperatures up to 3,500. Now, as everybody might know, that a pyrometer is, let's say, like a figure. So it is not a 100% precise measurement method, but since it is calibrated, we can believe on the temperature which are read and about the transmission and the epsilon, which is a very important value, and this is calibrated by our supplier. The second thing is there is, let's call it like a possibility to measure a melting point of tantalum. Tantalum has a melting point of about 3017 degrees Celsius, and there is a combination of tantalum with tungsten, and this melts between 2996. So we have a small temperature range, and I cannot go too much into detail because we work on this method currently, but we are very confident that the melting point of the tantalum in this case is accurate enough to show that the temperature was really 3000 degrees Celsius. And the third one is the XRD analysis, which Tom mentioned before. So there are already, let's say, references in the industries so that our customers are aware and they really know about that the furnace achieves 3000. And then if the XRD analysis looks very, very similar to the one which is achieved in, let's say, one of our furnaces or from another competitor, then there must have been 3000 degrees Celsius inside of the furnace. So there are some possibilities, but the question is really reasonable. Measuring temperature measurements at 3000 is very, very hard and not easy.
Okay, thank you very much indeed for that, Fabian. I've got a question here. It says, I'm reducing carbon, but I'm getting condensation in my work tube. How can I stop that?
Yeah, Tom, should I take over, or you would like?
You can take it if you want. Yeah.
Oh yeah, I just take it. To prevent condensation, what you have to do is you need to heat the gas outlet of the tube. If you have a tube furnace, you need additional wool or, let's say, blanket to insulate the tube, the outlet, and there also might be a possibility to heat it additionally with heat strips, or even with I don't want to call it heat gun, but this is mainly used in the laboratory. So this can be done. But on the other hand, you have to take care of the flanges and of the seals, which might become too hot. So in a tube furnace, it is not too easy. So that's why it is not mainly the 100% perfect choice. For a small scale, you can use it. But then I also would use some plugs, which just catches the decomposition products, so that these condensates are then introduced into this plug. It is like a soft plug or like a fiber which you put inside of the furnace, and this you just throw away.
Could you clean the plug afterwards? If you put the plug inside the furnace and flow air through it, you could effectively burn that all that condensate out as well, couldn't you?
Yes, it always depends on the condensation products, but yes, there are two possibilities. Correct, yeah.
Thank you. I've got one more question here, which is there a cooling system for the tube furnace to enable rapid cooling And also, I suppose with that, is there a sort of a recommended tube furnace for gas coating of active material on a lab scale?
Cooling. So again, I think we need to look at the process in a bit more detail. But you can.
Sorry, Tom, your microphone is gone again.
The microphone's very temperamental. It's because I looked away. Yeah, I suppose we need to understand exactly how they want to cool the material, because you could effectively remove the furnace from the work tube. So we've got instances where people are working with CVD style processes and they want to very rapidly quench the material. And you can achieve that by fitting the tube furnace itself onto a slide rail system and moving it over the sample and then pulling it away. Obviously, there's some safety aspects that you need to consider for this, and it's very much a home-built system, but we could definitely look at this.
Additionally, there is Tom, sorry, but additionally there is the IQ range, which we have in our portfolio. So if you need any information about that, there is an let's say new tube furnace range where we can give you some information about quenching or rapid cooling. So we really need to know about your process and what you really want to do, and then we can have a look into it and we can choose together the right furnace.
Okay, thank you very much indeed. At that point, ladies and gentlemen, I'd like to thank everybody for attending. I'd like to thank Tom and Fabian for their presentation. Any further questions that come in will be answered via email. And I would ask anybody who would like to participate in the Verda Scientific webinars this afternoon, a repeat of this morning's webinars, to go onto the verda-scientific.com website under webinars. You can sign up for any of the forthcoming webinars this afternoon from Ultra, Microtrack MRB, Wretch, or to hear this presentation again this afternoon. So thank you very much indeed for attending, and I'm going to end the webinar there. You will get a copy of the webinar via email. You'll be sent a link for the recording. Thank you once again, and we look forward to welcoming you to future Verda Scientific webinars.